Okay, I think we should be good here. Let's double check right now. Okay. Yep, I think that should about do it for now. Okay, so we'll come back once again. We are a little bit behind schedule, but I think we should be fine. So this is going to be another live stream where we are doing the 2023 AP Calculus free response question packet. So again, as before, we'll be going over all 6 of the questions and we'll be grading them accordingly. Let me just double check here. Yep. Okay. And so with that, we have ourselves the actual packet itself. Again, they're using the 2023 AP Calculus free response questions. And we'll be making sure we answer every single question and go through all of the problems together. And we'll be grading them accordingly. So as always, there are 6 problems here. And we will go through 2 at a time. In which the first 2 is going to be a calculator allowed section. So we'll be using the trusty TI-83 Plus graphing calculator, as it will show all the calculations that we need for us to answer the questions accordingly. Alright, very good. So without further ado, again, there's going to be questions on the packet. Given the space, managing things like that, all of the questions will be copied down onto the actual notebook that I have here on the side. Okay. And with that, we should be everything we need for us to begin this packet. Okay. As always, all the questions any sort of question can be sent to the email, the labcoatmath@gmail.com. And again, over there on the left side of the screen. And with that, we should be good to go to start answering some problems. Okay. Very good. So why don't we go ahead and begin, and we'll start with problem number 1. And again, this is the 2023 AP Calculus the free response questions. Okay. So starting here with problem number 1. For us to begin here, we have ourselves a table. So we have the row of t in seconds, and then we have the function f of t, which are going to be gallons per second. Okay, and it goes from 0 to 60 to 90 to 120 to 135 all the way up to 150. Okay. And then we go from 0, 0.1, 0.15, 0.1 again, 0.05, and 0. Okay. So, here we go. The actual problem itself says that a customer at a gas station is pumping gasoline into a gas tank. The rate of flow of gasoline is modeled by differentiable function f. Okay, and so yeah, and so we have all of that shown right there. Okay, based off of that table. Okay, so with that, we can get over to part A to see what they really want from us. So with A, it says that we want to use correct units. Using correct units, interpret the meaning of the definite interval, this time going from 60 to 135, f of t dt. Okay, in the context of the problem. Okay, and then they're going to continue with us saying that we want to use our right Riemann sum with the 3 subintervals and they'll give them directly to us. So we have 60 to 90, 90 to 120, and then 120 to 135 to approximate that value for that definite integral. The definite integral going from 60 to 135 f of t dt. Okay, good. So we've got ourselves our first problem right here. And so we can begin with our work, again, knowing that we're doing a right Riemann sum, but of course still understanding what the units will look like for the problem itself. Okay, so thankfully they already gave us the actual sub intervals that they want to use, so that one is not very much of a mystery. Again, Riemann sum meaning that we have to do the adding up of all of the bases multiplied by heights, right? And then we just have to add them up all over to each other. Okay, so with the first order of business here is that if we have a basis here for 60 to 90, that's going to be a base of 30 multiplied by, and again, so given that it's a right Riemann sum, so between 60 and 90 as shown on the table up there at the start, we're going to choose the right hand side equation. So out of the two, 90 will be chosen. Then from 90 to 120, 0.1 is chosen. From 120 to 135, the 0.05 will then be chosen. Okay. Well, Boaz Yang is saying that we need to turn on a light he can't see. Yes, I do believe that all of this is under a very bright lamp for me. I would say that, at least on my screen, it can be easily seen. Hopefully, Boaz can be a little bit more honest as to what he can see on the screen. But nonetheless here, we have ourselves all the heights that we need. So again, this first rectangle will be 30 multiplied by 0.15. Then we're adding that with the next base of 30, going from 90 to 120. So again, that is going to be the next order for the bases, multiplied by the height on the right side of 0.1. And lastly, the height here going from 100, let's see, so 90 to 120 to 135 here. The thing we must note is that the base actually changes from the standard 30 that we've been using before, from 20 to 135. It's going to be a base of 15 instead, multiplied by the height of 0.05, as we choose those right-hand heights for these rectangles. Okay, so because of that, we can easily throw this into our calculator, because this is question number 1, a calculator section. So let's have a look here, if we can see what the calculator shows itself. Good. So we go with the first 30 times the 0.1, and then we need to add that with the next 30 on the rectangle, multiplied by 0.15, and lastly, sorry, so it's 30 times 0.15. That's what we started with first, because that's what our work showed. Then 30 times 0.1 as the next height, and then lastly, we're adding that with 30 to 15, the last base of the rectangle, multiplied by 0.05, right? So this line of work is reflected 100% by the work that we have. So 30 times 0.15, 30 times 0.1, and 15 times 0.05. So all that is shown into our calculator there, and we get a total sum of 8.25. Okay. Now, the question did state though that we need to use correct units for us to understand how we're integrating this actual question itself for a definite integral of f of t. Remember that given that we're integrating something with the gallons per second, and we're taking the derivative in respect to time, okay, we have to make sure that we are going to deal with the fact that by integrating a rate, we're actually now reducing this back to the question about gallons, but it will be the difference of gallons pumped from the two time intervals from 60 to 135. Okay, so this is the 8.25 gallons pumped from 60 to 135 seconds. Okay. And that is going to be what the definite integral is asking for, and what the units will pertain in terms of the problem of the way that this gasoline is being pumped in the problem. Okay, quite nice. So let's go over to part B here. Okay, part B is asking that must there exist, let's see here, so must there exist is saying a value of C, okay, for the interval going from 60 to C to 120, okay, such that f prime of C must be equal to 0. Okay, and we need to justify our answer accordingly. Okay, so they're asking if we can confirm that we have between the interval from 6 to 120 seconds, that we have the first derivative of the function equal to 0. Okay, again, this is going to be the confirmation on this, right? So in that case, we're going to see what we can do in terms of the actual problem itself. Okay, so because they're asking that in specifically, so even though we might first think about, oh, mean value theorem, because it's specifically asking for the first derivative of C being equal to 0, actually this should be the clue. If you want to confirm such a statement such as the first derivative being equal to this, right, confirm such a value, okay, in that case, this is actually going to be asking us to be using our good old friend Rolle's theorem, okay, something that our students should be memorizing on their part as to what that means for them. All right, so Rolle's theorem, of course, on the statement, right, does the f of 60 be equal to the f of 120, right? That work requires the actual two endpoints of that interval to be equal to each other, and therefore we can then confirm that Rolle's theorem does exist, right? So if you look here, right, going from 60 is 0.1, and f of 120 is also 0.1 table, right? So the starting interval of 0.1 seconds, and then the end point at 120 seconds, ending at 0.1 gallons per second, right? So in this case, because both of those data points are equal to 0.1 in this sense, right? So that's a resounding yes on that part, okay? And because we know that, right, the f of t function itself, right, is differentiable, right? And that was stated directly in the problem. If you wanted to redefine that again, that we're differentiable function f across the entire time interval, okay? Right? We have then, on our own, have proven that the Rolle's theorem does exist. We have checked marked both parts that must be true for Rolle's theorem to exist. So we can then conclude, right, there must be a C in between the interval 60 to 120, such that the f prime of C is equal to 0, according to Rolle's theorem. Okay, so with that, we can go ahead and box all of that off with our work showing for it that we are using the theorem properly. We've proven that it is both differentiable and the two endpoints of the function are equal to each other, proving that there must be at least one first derivative being equal to 0 on that section of the function. Okay, let's go on to part C. It says here that the flow rate of gasoline in gallons per second can also be modeled by this new function g of t, being equal to t over 500 multiplied by the cosine of t over 120, all of that squared, for the interval going from 0 all the way to t going to 150. Okay, so it says here that using this model, then we want to find the average value of flow of gasoline over the interval 0 from t going all the way to 150. Okay, good. Very straightforward. That what they are looking to do over here, right? That we want to find the actual average value of the function. And this time, again, this is the average value of the function of g of t, this nice equation that they gave to us. Okay, average value, of course, meaning that we have to bust out that lovely average value equation. All right, so average value in this case will be equal to the interval going from that time interval. Again, for us will be 0 to 150 for us. All right, so 0 to 150 of g of t dt. But we cannot forget that from this, we are then multiplying all of this with the coefficient of 1 over the difference of the time intervals, because we're dividing it over the amount of time that was spent to get the average value across the entire function as such. Okay, so with that, if we want to go ahead and see how this will look like if we want to plug this directly into our calculators here, is that it will be 1 over 150 as a coefficient multiplied by the interval from 0 to 150 for g of t, which was the actual t over 500, and then multiplied by the cosine of t over 120, all of that squared, taken in reference to t for that. Okay, so we can run this through our calculator and we can get a result for our average value equation. Quite nice. So if we go use the function integral, so if we go ahead and use the function integral operation for this calculator, we can get everything set up here. Starting with the equation, we can use the variable of t here. Okay, divided by 500. We multiply by the cosine of all of, let's see, so it's gonna be t again, divided by 120. But all of this will be squared inside of the function itself, okay, of the cosine function. Then we will evaluate this from t all the way from 0 to 150. Okay, now for all of this, so we still need to remember we have to multiply by that coefficient of 1 over 150 after the integration for this to then actually be the proper average value of a function. Okay, so we run this through and we get the result of 0.0956 or 60 if you round it properly. So again, the 9 will go to a 10, so 0.960 if rounded properly. So let's get that started here. So it's 0.960. Now, because again, this is average value of a function g of t, the average value does not change the units one bit because it's the actual value of the function itself. So that'll be still in gallons per second, as that was the flow rate of the pump itself. Okay, and I gotta remember to make sure we actually have the extra leading zero there. So 0.0960. If that doesn't look proper, let's try that again. So do the calculator 0.096. This is going to be gallons per second. Again, we're going to 3 decimal places for the most part as the best means of showing as much as we can on this type of problem. Okay, very good. Let's go over to problem B, and this should conclude for question number 1 on this problem. Okay, so it says here that we are using model G, okay, defined in part C. Okay, we want to find the value of the G prime of 140. Okay, interpret the meaning of the answer in the context of the problem. There you go. All right. So very simple for part D here for this last bit is that we need to do G prime of 140. Okay. And so with that, we will have our work cut out for us. Okay. This value is very easily done, of course, is that we just then can easily put that right into the calculator, right, of the actual plugging in of the function itself. So from the calculator, if we want to show that, I think we should be fine. We can go ahead and do, I think if you want to show for the test graders that we're doing everything in terms of the book here, we can put down the G function. So 20, all that squared. Again, we're evaluating this in terms of derivative with respect to t, and where t is equal to 140. If you want to do it that way I think would be the best way of showing to the test graders that we are going exactly for the first derivative right there. Okay. And so with that, we can go ahead and do, in this case, the function derivative equation on the calculator, as we can find a derivative of any single point with this operation. So we're going to go back again. This time is going to be t, no, that's a y. T over 500 multiplied by the cosine of all of t over the 120. All of that squared for the t function. Okay. And then this time we're going to evaluate still for the variable of t, but only evaluating at a single point of 120 for the derivative. And we get the actual response of negative 0.0023 if we round that properly. Okay, so negative 0.0023, and the units in this case will be gallons per second squared, as we took the derivative of the time value again. All right, so if we want to then explain it as to in the context of the problem what that means, okay, right? So the G prime of 140 would mean, right, that's the change in the rate of gas being pumped, right? Of course, if we take a rate of gallons per second, take another derivative, we are then monitoring the change to see how the actual change in the flow rate itself is either increasing or decreasing, right, for the gallons per second itself. As we can see, again, using this, both the G prime and the regular function G, it can be used for things like speed up and slow down, as many times were asked in previous questions. But nonetheless, though, that's all that they wanted for us to show, is that we understand, or at least give a good explanation as to what the G prime of 140 looks like in this case. Okay. Epic Gamer Carablast says, how? Yes, how in the sense, if we can get a bit more context into your question, as in like how we get our answer for the negative 0.0023, or in terms of how we actually interpret what that means for the problem. Because in either case though, if we are able to actually go to this problem, right? Again, this was a simple one that we just had to plug in directly into the calculator. Shouldn't have been so hard. And so again, this is more of a copy and paste of exactly what the calculator spat out to us. But because the question was asking for us to give the answer in the context of the problem itself, right, we needed to make sure we actually put into words what the gallons per second squared is, right? Because we do increase another time value because we took the derivative in respect to t down in the denominator. So again, if it's gallon per second, think of it like gallons per second multiplied by another per second, right? Again, this is going to be another rate of change for the gallon per second rate that we have already given, right? So again, as we said already, this is going to be a change. Again, another set of change, but in this case, not just the actual amount of gas being pumped, but it's the change in the rate of gas being pumped into the car as the problem first dictated. Okay, so I think with that, hopefully that answers your question if you were referring to question D here. But we should have everything we need to then go ahead and move over to question number 2 for this problem, so that we can go and finish the section of using the calculators, and we can begin our grading process of this exam. Okay. So, question number 2 here, to start off with the context here, there's that. It tells us that Stefan swims back and forth along a straight path in a 50 meter long pool for 90 seconds. Okay, and so it says Stephen's victory is modeled by not victory, that's wrong. Its velocity is measured by the function v of t being equal to 2.38 multiplied by e raised to the negative 0.02 times t up on the exponent spot, but we still then multiply it by sine back down of pi over 56 multiplied by t. Okay, and again we have t in seconds, t is in seconds, and v of t is in meters per second. Okay, quite interesting as a way to then show a velocity function, but that's what we have so far. Okay, so then we have part A here. It is asking to find all times t on the interval 0 to 90, at which Stephen changes direction. And then we need to give the reason for that. Okay, so very good for our starting question here, right? If you want to change in direction, what that is implying, of course, is that we take the velocity function graph, right? And then if we cross the x-axis, right, that in turn would mean that it is a change in direction. Right, of course, the sign change from positive to negative or back again from the actual x-axis, as that can be seen, is going to be enough to determine that we have changed directions on our path here. Okay, so we can go ahead and clear out for our graphing right here, and we can plug in directly for the velocity function that they gave us. So it's a 2.38 multiplied by e raised to the negative 0.02 multiplied by the variable of x. We have to go use this x instead because we're graphing on the xy plane right there. And then we multiply then by the sine of pi, sine of pi over 56 multiplied by the variable of x again. Okay, so that is the entire velocity function shown right there on the actual part of the equation right there. So the best case scenario is that we can start at -1 and we going all the way of the interval again, going all the way to positive 90. So I think 91 will be fine, doesn't really matter in that sense. But because we're looking for just crosses on the x-axis, we can limit y's to like -1 and positive, or maybe 2's, so that we can get a nice full picture as to what this looks like. Okay. So as you can see, we are starting and it looks like we changed direction once. And if it goes back up, no, it doesn't. So it looks like there's only real one, because this entire interval was from 0 to 91. So it looks like I have to smack the camera, of course. But there's only one time in which we have an actual change in direction. So we can go ahead and calculate for that. Again, the 0 of the actual function right there. Okay. So we go from the left side of that, and over to the right side of that, and we'll tell it to take a guess. And at 56, 0, that is going to be the time. So 56. So at the t is equal to 56, again, the velocity function was going from positive down into the negative region as a change in that direction. Okay, so that should be pretty nice to get started with. If our camera can focus on that for us. Okay. All right, so that's pretty nice. And so for that to get started with over here, we can go ahead and see that the reason, we have a reason that we crossed the x-axis there. Okay, so it says here that at the t is equal to 56 seconds, Steven changes directions from the positive to negative, right? And our work shows that we have graphed it and we're looking for the crossing of the actual function on the x-axis to confirm that change in direction for us. Very good. So let's go over to problem B here. Problem B is asking that we want to find Steven's acceleration at the time is equal to 60 seconds. Okay. And then show the setup for the calculations. And indicate units of measure. Okay. Am I going off of the line there? No, I'm not. Okay. And then they're asking then, is Steven speeding up or slowing down at the time is equal to 60 seconds. Okay. And then giving you the reason accordingly for that. Okay. So that's quite an interesting problem here, right? So acceleration, of course, it means that we have to, if you want to go the acceleration of any sort of function, that's going to be the velocity's derivative on that time. Okay. So because of that, we have the acceleration at 60, means that we have to take the derivative at 60 seconds for us. So we can do that straight away from our calculator. So going back, we can go use the math function to go to the function derivative operation right there. So by putting in, once again, directly into the calculator, 2.38 multiplied by e, let's see, e raised to the negative 0.02, and we can go here with the equation, the variable of t there for that case, multiplied by the sine of pi divided by 56 multiplied by t again. Okay, again, closing that off, we're going to go with the variable of t for this, and exactly 60 for that variable. Okay, now they're yelling at me for a reason here. We closed off the sign, we closed off the, what the heck? Okay, sorry. I put a question mark for the reason. That's not right. That's the just e raised to the 0.02. Okay. I don't know how I managed to get a question mark on my graphing calculator, but that is going to be the correct first derivative of the velocity function, which would be acceleration. So that for us would be the negative 0.467. In this case, if it's going to be acceleration, that's meters per second squared for the actual units for the acceleration function. Okay, so because of that, we needed to go again. Remember that if you want to do any sort of evaluation for speed up, right? So speed up versus the slow down, right? Is that the acceleration and velocity at that time needs to be both positive or negative, right? That will indicate a speed up for ourselves, or in a slow down, that's the acceleration and velocity. Again, one positive and one negative. All right, with them having different signs, that will be enough for us to mathematically show that we are slowing down instead. So, because this is going to be the A acceleration in 60 seconds for us, which is still part of our answer that they want us to solve for, that's 60 seconds, all right? So, the velocity at 60 seconds can be easily proven either through the actual okay, sorry. Looks like there were some issues earlier, but I think we should be fine. Yeah, I think the stream was dying there for a second. But I think we should be good here for our side. Okay, so going back to it though, if you want a quick recap, if any information was lost here, is that we were going over the speed up and slow down evaluation for that specific acceleration at 60 seconds. And so we need to know the velocity at 60 seconds, so we can either plug it in, or thankfully, because we already graphed the function, we can actually look at the table here. So if you want to set the table at exactly 60 that we want to show here, we can actually look at the table for the function that we already have, and they give us that exactly on the value at 60 for the variable of t, and it will give us negative 0.159, so 160 if you round it accordingly to the third decimal place. Okay. So negative 0.160 meters per second is going to be the velocity at 60 seconds. And would you look at that, both of them are negative, so we can conclude that Steven is speeding up at the time is equal to 60 seconds. Okay. And the work is shown. Now we've done the comparison between the acceleration and the velocity for this part, such that we get the total of the two parts that they wanted us to answer for that problem. Very nice. So let's get over to part C here. And we already did everything that they asked for part B. So part C then follows up here that we want to find the distance between Steven's position at the time is equal to 20 seconds, and his position at the time is equal to 80 seconds. Okay, and of course we need to show our work accordingly to match their demands on that. Okay, so because of that, let's go ahead and see what this will look like in terms of this problem. Okay, so again, we want to know the distance between two positions, right? So what does that sound like for us, right? Because we only have, as I know, we only have the velocity function on its own, right? So we need to give that a little bit of thought for a second. You realize that, that must mean that we are doing the fundamental theorem of calculus for our work, because, and if we took the definite integral, because we have two exact time points in which they want to find the difference for, right? So from 20 to 80 seconds for that velocity function that Steven is swimming through. Well then, given the fundamental theorem of calculus, we then understand that we are dealing with going backwards to the actual position, right, of 80 minus the position at 20. Well, that's pretty nice, right? Because from that, that's actually the difference that they want, and this definite integral is exactly what we want to do for ourselves. Okay, so because of that, we can then set up the definite integral by plugging in for the equation itself and throwing that right into our calculators. So 2.38 multiplied by e raised to the negative 0.02 times t, all that multiplied by the sine of pi over 56 multiplied by t inside dt. Okay, so as you can see, this is a very easy way for us to actually understand how fundamental theorem is used to find the difference of that first integral for that function. Okay, so let's put that all through our calculators here. I think we can kind of work around it, but it's fine. We can start at the beginning. So we take the function integral operation right there, and we then will start plugging in for the VFT function itself. So it's 2.38 multiplied by e raised to the negative 0.02, and again that's for the variable of t for that, and then we multiply that by sine of pi divided by 56 multiplied by that variable of t again. Okay, so that is the entirety of the velocity function inside of there. Okay, and then we will then evaluate this for the variable of t, going from the two time intervals. Again, now I have to show this properly, so it's 20 to 80 seconds, right? Okay, so it's not 0 to 90, it's 20 to 80 as what they wanted from the actual equation itself. So by throwing all of that together, we get a total difference of 23.384 if rounded properly. Let's put that down. So 23.384. And again, because this is a difference in actual position, right? So this is a position minus a position. And we need the calculator to focus up here. There's plenty of light for you to focus on, Mr. Camera. Okay. Okay, there, that's better. All right. So position minus position right there. So again, we're still just dealing in terms of meters for the difference between the 2 points, right? Again, the difference in position, so the actual distance that he traveled between those 2 parts is going to be 23.384 meters for this part. Okay, fairly simple enough. Okay, but then part D then says that we want to find, right, the total distance. Steven swims over the time interval from 0 to 90 seconds. Okay, and of course show the work according for that. Okay, so total distance, well, that's going to be quite something, right? Total distance is going to be a measurement. Again, now, even though we will take the integral of the velocity function, right? Total distance will then mean that even if we go from 0 to 90, we need to then take the absolute value of that velocity equation that we have and stick that into the interval, again, because this is mentioning total distance. Okay. Again, total distance being the actual amount. Again, absolute value is going to be important because we swap all the negative values for the result of the velocity back into positive ones so that we can add everything up together instead of canceling anything out because Steven changed directions. Okay. Again, the actual notable amount would be different because anything that if Steven is swimming forwards and swimming backwards, right, in terms of his actual trajectory during his swimming session, is that it starts canceling out each other if we just took the normal derivative, and so the absolute value is very important for us to keep intact for on this time. Okay, so with that, we can then just plug right in for the velocity function inside of the absolute value. So that's going to be 2.38 multiplied by e raised to the negative 0.02 multiplied by t multiplied by the sine of pi over 56 multiplied by t dt. Okay, so that should go ahead pretty nicely. Okay, so with that, we can then put into our function integral now. So put into our function integral right there, but we must also then go in terms of the number part of the calculator that we're doing the absolute value now. So making sure we swap all the negatives into positives for the function of the 2.38 multiplied by e raised to the negative 0.02 multiplied by t right there. Okay, and all of that multiplied by the sine function of pi over 56 multiplied by t again. Okay, again, all of this still evaluated for the variable of t going this time from 0 to 90, so the entire length of time in which Stephen went through. And of course, we need to try that again because the absolute value requires another parentheses to close it off. There you go. Okay, so this is the way that we have slammed that entire absolute value into the actual function itself, right? So again, we're doing the absolute value of the velocity function so that we can then measure total distance. So it'll take just a minute here because the calculator is really slamming some numbers and functions together on our behalf, and we should be able to get our total response here. Okay, so for those that are listening, if only, you know, we had a couple of users, so if our viewers can very easily slap that like button while we're waiting for this result right there, I think we should be good to go. So 62.164 will be the actual amount that Stephen swam in total here. Okay, now the calculator gave us 62.164. Okay, this is going to be, if it's total distance, that's just going to be still measured in meters. Okay. And that's how much he swam in total. Okay. Again, this is just a simple recollection of the actual total amount that he swam. And with that, we should be good to be completed on problem number 2. Okay. Now, let me try something here. I wonder if... No. Okay. We'll actually get back to that in just a second here. I wonder if we can try for... No, we'll have to get back to that later time. Okay, so I think with this, I can show you what I'll be using. Again, for all of these, so if we go back to problem number 1, and we'll start our correcting process here with my trusty red pen right here, okay? So we're gonna go back to problem number 1, and we're gonna start correcting that to total up the amount of points that we have received across the entire packet so far. And so I can swap over to my other screen here, is that we have the actual complete scoring guide for the calculus test, right? The 2023 exam that we're doing. And so we'll be looking down and we'll be correcting all of the points in which that we have gone over. Again, they'll tell you exactly what will score based on what needs to be shown on the exam every time. So we'll start with problem number 1, and we'll go down back to the notebook here so that we can see through all of the work, again, what is exactly needed for our side right here. Okay, so to begin with, in part A, it's saying that we need to use the correct interpretation of the meaning for the 60 to 135 for ourselves. Okay, so us showing the actual Riemann sum properly, right, that we run this through. So in terms of the form of the Riemann sum, right, again, of the base multiplied by the height, again, that being multiplied all the way across, right, we do get the actual total amount of 8.25 gallons. Again, that is the correct answer, right, and the way that Riemann sum is formed. Okay, and so the units, of course, is the number of gallons pumped in between that time interval from 60 to 135 seconds. That's exactly what they're looking for. So part A will grant us all 3 to 3 points correct for us on that part. Okay, then part B will continue. That they wanted to show for us to confirm that the f prime of c value of being equal to 0 is going to be existent for that table of values that they gave us. Okay, so they use mean value theorem. They could use, or they said or Rolle's theorem, so either would work. So my idea that Rolle's theorem is going to be correct to show that, again, work-wise, that if these 2 points were equal to each other, the ending points of that interval, right, and given that it is a differentiable and continuous function, again, both continuous is within the umbrella of differentiable, there's going to be confirmed that there must be a c within that interval such that that first prime f prime of c is going to be equal to 0 according to Rolle's theorem. So both, again, our setup and our actual work itself with our conclusion will give us all 2 out of 2 correct on part B. Okay, moving on down to part C here is that we want to do the actual flow rate, again, average value for this, meaning that we do have to set up accordingly that it's going to be the 150 of multiply 1 over 150 multiplied by the integral of the definite integral of the function of g, as stated right there. Again, that's the formula that we must recall. And by storing that into the calculator by 0.096, that should be in gallons per second. That's exactly what they wanted to see. So with that, we get the total points of 2 out of 2 correct again for part C this time. And then lastly, going down to part D, and that we need to do the interpretation of g prime of 140. Again, this was very simple. We just have to throw that right into the calculator, and we get a very interesting different response here, looks like. That's quite something. So 0.005 is what they're telling us that we should have gotten. Well, let me actually run that again to make sure that I haven't lost my mind here. So let's go again. Let's take the derivative function of that g function itself. So that's going to be the function that they gave us. So that's going to be t over 500 multiplied by the cosine, all of t over 120, all of that to the second power, closing that off. We're taking that in the value of t at 140. Okay, they gave me a different response than what I had. It looks like I actually threw that incorrectly into the problem. So let's see. Can I see if I can recall back? What in the world? Did I just copy down the wrong point in the problem? Well, that's kind of sad. Okay, well, that looks like that will be a lesson in making sure we actually put everything down properly, because that actually should have been the answer. Even my calculator gave it multiple times for whatever reason. So that's going to be unfortunate that we got the actual copying down. Like literally the entire setup was exactly the way it should have been, that we threw directly into the calculator. And the actual interpretation though, right? Okay, we're looking for the change in the rate that is being pumped, right? For this part, so that's still going to be correct. So we still at least get 1 out of 2 correct, right? Because we understand what the g prime of 140 means. That's a little bit unfortunate that we missed a very simple copying down of the problem itself into this, but that is still a very good reminder for us to actually know what we're copying down onto our answer sheet for the test graders to know that we actually understand what we're doing here. So because of that, we only get 8 out of 9 correct on this first problem. Very sad we couldn't have scored 100% because of a very simple mistake. But nonetheless though, let's go ahead and put that down onto our front page here. So given how we're scoring, question 2, question 3, 4, 5, and 6, we can still keep our hopes up to scoring still fairly high, even though we scored 8 out of 9 on that first part, because a very sad, simple mistake. Oh, yeah, I should really get a soundboard. I think that might enhance our ability to study. Maybe just a little bit if I can get to that pretty soon. But nonetheless, though, we can go over to question number 2 and start correcting that before we move on to the second part of this problem, this packet here. So again, this is the even switching, changing directions with the actual swimming that he's doing in a straight line. So because of that, we are looking for the v of t graph again, and we want to change the direction in the change of sign for the velocity. So that's what they wanted for us to confirm that that was the case. And at 56 seconds, that's the only time in which Stephen does change directions. So with that, that's 2 out of 2 correct for part A. Okay. Then let's move on to part B over here. That the acceleration is going to be given at a specific time. And what is happening? Why am I really messing everything up here? Let me go back here. It's the acceleration they're telling us needs to be negative 0.036 according to that. Okay, so let's bring this all the way back here. That's as far as it goes. My calculator doesn't tell me. Okay. That's unfortunate. All right, well, let's run this back one more time to see if I actually get the correct units. This is becoming very odd, at least what's happening in this problem. So we are running the function derivative over 2.38 multiplied by e raised to the negative 0.02 multiplied by t, all then multiplied by the sine function of pi, that's h, pi over 56 times the variable of t again. Okay, so all this again in terms of variable of t at the point of that's gonna be at 60 for this. Okay, my calculator very conveniently forgot how or exactly what I put down the first time. So that's a little bit disheartening, but this is actually going to be the correct value. So again, that's another sad mistake, at least on our part, that the acceleration at 60 was not correct. Okay, so that's kind of sad, right? But we still get a point for acceleration units. That in itself is something that they're just looking for directly, the units themselves. So we don't score on the actual answer of a of 60, but the units itself will score your point by me mentioning that it's meters per second squared. And because our velocity, now that's still correct, right? That was taken directly from the velocity graph that we graphed first at the start of the problem. And because the actual, still the sign is thankfully still the same as our wrong answer, we still end up with the same conclusion, that because the acceleration and velocity are both negative at time of 60, Stephen is still indeed speeding up at that time. Okay, so even though we missed one, that's going to be 2 out of 3 correct for this part. Okay, a little bit sad that, again, for whatever reason, our calculator work is not as clean as it should be, but still a good lesson to make sure that we're still very careful about what we're doing on this exam. Okay, then moving on to part C here is that we need to then find the distance between the Stephen's position from 20 seconds all the way to 80 seconds. Okay, so of course we need to show that we are going to instead use fundamental theorem to understand that by taking the definite integral from 20 to 80 seconds, we are looking at the difference between two position points that Stephen swam across. And because of that, right, we can actually go ahead and look at the result directly from the calculator, and this time at 23.384, that is indeed going to be a proper way to actually put something nicely into a calculator. Amazing! I didn't make a mistake this time. So because of that, again, this is a simple plug-in by understanding how to find that distance between two position points, thanks to the fundamental theorem of fundamental theorem of calculus right there. So that will be 2 out of 2 correct on that section as well. Yes, we have our loyal follower, Miji Yang, saying that she's watching this from New York. Ah yes, she gets to be 3 hours ahead, but she's still coming in to see how well we are going to perform on this exam. Yes, thank you for still staying very loyal to this channel, all the way from the other side of the country. But with that, we should be finishing up our corrections of part D right here. That we want to find that total distance. So of course that exactly meant that we need to take the integral of the absolute value of the velocity function in respect to time. Again, we're still going from 0 to 90 seconds, so so that new limits from 0 to 90 is going to be very important to show. Okay, and by plugging that straight away through, we get the actual answer of 62.164. So that is also good. Finally, we're making a little bit of headway into not making mistakes into plugging things into the calculator. So that is going to be all 2 out of 2 correct for us understanding what total distance means, and that we need to shove in the absolute value into the calculator for us to be able to do that. Okay, so with that, we've gotten everything except for 1 correct, so that'll be another 8 out of 9 correct on this section here. Okay, so that's another 8 out of 9, another all, because we missed something that should have been very simple for us. Literally our work and our units were all there, just copying things incorrectly from the calculator. But we're making good headway. That is still, at least we can still aim for a high score if we keep our wits about us and making sure we don't make any other silly mistakes moving forward. Okay, very good. So we have everything we need. Let me switch back over here. All right, we have everything that we need then to move on to the next part. So we'll do questions 3 and 4 together before going back to another correction here. Okay, so okay, so looks like here on part 3, So let's start with question 3. Looks like they're throwing us already directly into a slope field question. So also actually something I need to remind myself is that questions 3 all the way to the end of the exam where we'll not be using the graph calculator. This will be thrown off to the side as that is not allowed for these problems. But nonetheless though, at question number 3, we have a slope field problem. So we'll get to doing this shortly after we copy over the problem first, because the rest parts B down to D will not be using slope field. Again, this has to be drawn directly onto the packet. So we'll put this back on the camera once we're ready to do part A. Okay. But nonetheless, so let's copy down this problem here. That at question number 3, it tells us that a bottle of milk is taken out of a refrigerator. Okay. And placed into a pan of hot water to be warmed. Okay. The increasing function, capital M, models the temperature where M of T is in degrees Celsius and T is in minutes. Okay, since in the pan, of course. Okay, so we have the differential equation dm over dt is equal to 1 over 4, all multiplied by 40 minus m. Okay, and they also tell us at the time is equal to 0. The temperature is 5 degrees Celsius. Okay, and it can be shown that m of t is less than 40, okay, for all values of t. Okay, so quite nice for us to get started out here that we've got our differential equation and a starting point. Of course, this alludes to the fact that we're going to have to do some separation of variables, but let's not get ahead of ourselves. Let's first get to part A, which should be done on the packet, as this is a slope field. Again, slope field kind of problem, which is a bit too much for us to then copy each individual tick mark onto the packet itself. Okay, so we have ourselves the slope field right here, okay, of the entire function, again, of the dm over dt differential equation as shown. So we want to sketch the point through 0, 5, right? So starting there, that's right back over there, okay? And let's see here. We are saying that there's no data on this, but okay. I don't know. But nonetheless though, looks like my streaming deck is being a little bit weird right now. But nonetheless though, I think we should be fine for this part. So again, there we're looking to sketch the solution through the point 0, 5, and that was marked down there. So because of that, we are going to follow along with the increases of the function again. So we're increasing, if you look like, and then we actually go to a 0 slope. Again, we're edging out to a 0 slope as you reach the asymptote going through that side. Okay, again, because it's the hard 0 slope coming across that line, again, this the 40 degrees Celsius mark again, right? It needs to be, it did tell us before that we are going to be underneath 40 for all the values of time, right? So we will not touch the 40 degrees Celsius mark. We're going to get close to it as we increase, but we will settle down underneath that value for that. Okay, I think that's pretty good for a possible solution curve. I think we'll be fine for that. So with that, that's all that part A was really asking for. Again, for you just to sketch one possible solution curve going along that slope field, following those tick marks as to how we're going to be changing the direction of the actual function itself. But with that, we should be good to then get on to part B. The part B says that we want to use the tangent line line at e is equal to 0, m of 2. Okay, again, so because of that, all right, the tangent line at t equals 0 means that we have to use the tangent line equation, right? So tangent line equation, okay, is that we would do the y is equal to the slope of x minus h plus k on the outside, okay, where again the h comma k is the point at the x is equal, or sorry, t is a variable, so t is equal to 0 point, again, because they want to use that as a starting point. Us knowing that if t was equal to 0, that's something that the problem gave us, right? The temperature of the milk is 5 degrees Celsius at the time is equal to 0 point here. The 0, 5 is going to be the result of that, okay? So in that case, all we need to do is that we have h and k, we need to know what m is, right? The actual slope at that given time. So because of that, we can then go dm over dt is equal to 1 over 4 of 40 minus capital M. And we're going to measure this in terms of the t is equal to 0 and the m is equal to 5, the temperature of the milk at that time. So the slope in this case is going to be 1/4 multiplied by 40 minus capital M of 5. So in this case, it's 35 over 4 as a result. Okay, again, this is going to be degrees Celsius per minute as the actual rate equation. Again, dm over dt we measured in those units. So we can throw all of this together on this side. So the actual equation is equal to y is equal to 35 over 4 of x minus h being the 0 and then plus k being a positive 5. Okay, and it's because of that we need to approximate actually for the time is equal to 2 case for our part here. Okay, so because of that, so if we go m of 2 for that function, right, being evaluated at a specific point, that's going to be 35 over 4 multiplied by a 2 plus 5 on the other side. Okay, so by canceling out, that's going to be 35 over 2 instead, plus 5. If you want to make it a decimal, this is going to be the 17.5 in that case, giving us m of 2 being approximated at the 22.5, or if you want to leave it in terms of the fractions, again, 5 is 10 over 2. So it will be either the 22.5 or the 10 over 2 makes it 45 over 2, both of which should be fine. Again, this is going to be the degrees Celsius per minute as the units for that. Not per minutes, no. It's just degrees Celsius. Capital M is going to be just the temperature of the milk. We're approximating that at the 2-minute mark. Okay, good. So that should be the way that we do this type of problem. Again, understanding how we can use the tangent line, right? Again, with a very distinct formula, knowing that if you find the point and the slope at the specific time marked, then we should be able to then get to the actual evaluation of some estimations of a time in which they be the starting point for. Okay, so with that, we can go over to part C here. Okay, that they're going to tell us that we want to write an expression in this case for dm squared over d squared t, so the second derivative in terms of capital M. Okay, so we want to use that second derivative dm over dt on the second derivative to determine whether the approximation from part B is an underestimate or overestimate for the actual value of m of 2. Okay, and of course we need to give our reasoning accordingly as well. Okay, all right, So we're taking the second derivative. Again, this implies that we're going to do implicit differentiation, given that the first derivative of m is not going to be 1. The first derivative of m was already given as the 1 over 4 40 minus m. Okay, so let's get started with that. We have the first derivative only. Okay, so that's going to be 1/4 of 40 minus capital M. Okay, and again, we need to take the derivative in terms of t a second time as well for this. Okay, but something I like to do before I go ahead and do that is to make sure we can FOIL out or distribute out the 1 over 4 coefficient such that we can end up with an easier part right here, so 10 minus m over 4, and all of this will have its derivative taken in respect to t for that to happen. So because of that, the 10 will go straight over to 0. So we get the negative 1 over 4 coefficient waiting for us as we take the derivative m in respect to t as the second derivative. Okay, so with that, we should be able to then go and replace that dm over dt, because something that we already do know earlier in the problem. So that's going to be negative 1 over 4 multiply all of another 1 over 4 of 40 minus m. Okay, so with that, we should be able to have everything that we need so that we can then start simplifying all this out. So that's negative 1 over 16 of 40 minus m. And then from here, we can then put in the, so 40 over 16, that they have a common of 8. So it's negative 5 over 2 plus m over 16, right? And that will be the second derivative of the dm over dt rate. Okay, so very simple algebra to clean everything up right there, but that should be good enough for us to keep going from there. Okay, so with that, then we need to then describe if that's approximation is over or underestimate from that value, right? M of 2, right? Okay, so again, we can keep track of that curvature for ourselves, right? Given that the m of 2 was approximated, or I think it's m of 0. So you look at the curvature at that point and how we are going. M of 0 being equal to 5, as was from the problem, right? We can then take the second derivative, so d squared m over dt squared, right? At the m is equal to 5 point. So at the negative 5 over 2 plus a 5 over 16, right? As a result from that, okay, we can then put in the fact that the negative 5 over 2 multiplied by another 8 will be negative 40 over 16 plus 5 over 16, making it a negative 35 over 16 as a result. Again, this is going to be a concave down type of second derivative that we're dealing with. And so because it is concave down, and right, given the fact that we have the first derivative, so again comparing that with the first derivative, so the dm over dt at the m is equal to 5 point that we've done earlier in the problem, again plugging in for the m is equal to 5, we got a 35 over 4. 35 over 4, again that's going to be an increase, right? So the function is increasing and is concave down. So on our part, what that would mean for the actual approximation, right, if we want to make sure we can get it kind of looking on our sense, right, because we're increasing and concave down, means that we're doing this kind of a function, right? Okay, so if we were then approximating the actual values for that, as you can see, right, because we're increasing and our concavity is downwards for that, okay, we are then showing that we are dealing with an underestimate. Right, for those points as we come across the actual part of this integration. Okay, again with the actual tangent line, again going at 0 is going to be underneath that part right there. Okay, again in this sense, if it was decreasing, then right, the actual estimates will be above it, but because we are increasing and that is concave down, right, then that will show us that we are doing an actual underestimate of that point, right? So yeah, okay. So with that, we should be good enough to keep going forwards from here, right? So let's just make sure. Yeah, okay. So actually, let's actually double check that. So because we are concave down and increasingly, we should draw this a little bit more exaggerated to see, right? So we're going with a curve kind of like this, okay? And we are tangent to a specific point in that, right? So we were estimating, right? Again, beyond that point, right, going forth. And again, that is actually going to be above the curve itself after we keep increasing away from it. Okay, so in this case, it actually turns out it's an overestimate, right? Again, going from both of our conclusions that we're concave down and increasing with a graph shaped like this, right? That will be an overestimate of the actual values of the function, and that will be the case of m of 2 in part B. Okay, so let's go finally to, oh my goodness, man. Maybe I could. We're getting some losses here. I wonder if we can change this really quickly before we go to part D here. Yeah, okay, I don't think I can change that right now, but I'll have to keep that in mind for later. 2500. Okay. All right. Nonetheless, though, let's see how we can finish up with part D over here. So that we can get through problem 3 and we can move to number 4. Okay. So part D says that we want to use separation of variables. Okay. To find an expression for m of t. Okay. Again, with the particular solution of m of 0 being equal to 5 degrees Celsius. Okay. Very good. So, because we're doing a separation of variables for this, right, we need to go ahead and start our integration process, starting with dm over dt being equal to the 1/4 multiplied by the 40 minus m. Okay. So because of that, we need to make sure that all of the parts of the equation with m must be sent to the dm side, while the dt side needs to move over to the other side with the t's. Again, this is going to be separation of variables right here. Okay, so with that, we can go to the next line here that we have dm over 40 minus m waiting for us, and that's equal to 1/4 multiplied by dt. Okay, with that, again, by matching the variables on one side with the other, this is how we can confirm that we can do integration, the indefinite integration, on both sides of this equation. Okay, so with that, we can then come up with the solution set that the natural log of the 40 minus m, and because there's a minus m in that statement right there, right, we need a negative waiting for us on the outside. Going to cancel that negative coefficient waiting for us, and it'll be 1/4 t plus c as we integrate a simple 1/4 constant. Okay, again, the constant of integration is very important. They're going to yell at us if we don't put that in there as the result of the indefinite integral. And so with that, we can then solve for it. So again, we're going to make a note that we're solving for c. Okay. So by solving for c here, we are going to then plug in, again, we have m of 0 being equal to 5. Okay. So because of that, we have the negative natural log of 40 minus 5 being equal to, the time is going to be equal to 1/4 multiplied by 0 plus c. So because that c is going to be equal to a negative natural log of 35. Okay. Very easy for us right there. And so with that, we can then plug everything back in here, right? So the negative natural log of 40 minus m is equal to 1/4 t minus the natural log of 35. Again, as that c is plugged back into the position where it once was. And now we must isolate for m such that we can get our result here. So first off, we can clear off that negative integral, right? The negative coefficient, so we multiply everything by -1. That will be a positive natural log of 40 minus m is equal to the natural log of 35 minus 1/4 times t. Swapping that over to the other side. Okay. And so with that, we can then raise everything to the e exponent power, such that we can cancel out those natural logs on either side, starting with the natural log 35 and the 40 minus m. So we get 40 minus m is equal to 35 multiplied by e raised to the -1/4 times t. And lastly, by subtracting 40, and then by multiplying by -1 after the fact for the m, we will then end up with our last full equation for the m of t being equal to a positive 40 minus 35 e raised to the -1/4 times t. Okay? And this will be the result of integrating and doing everything properly algebraically such that the m function is now isolated on its own. Okay? So that is quite nice. Okay? For that, and so we should be good now to move onwards to problem number 4 after finishing our integration. Okay. All right, very good. So we can go forth here. Now problem number 4 is now asking with a question with a lovely graph attached to it. So let's get this copied on over. Okay. So we will go up a value of 2 and across 8. So starting here, this. Okay. So let's go back here. Okay. So we go 1, 2, we go 1, 2, and go across 8. So 1, 2, 3, 4, 5, 6, 7, 8 right there. Okay. So at -2, comma +2, -1, comma 0, going all the way to 2 down there. So that's the first line segment right there. Then going up to 2, comma 0, so right there, all the way up to 4, comma +2. So that all goes up right there. And then up to 6, comma 0. Okay. And all the way up to 8, comma 2 again. This is going to be a semicircle right there. Okay. And as a note, this is the graph of f prime. Okay. That they clearly stated right there. Okay, so it says here that as part of the context is that the function f is defined on the closed interval going from -2 to +8. Okay, and satisfies f of 2 being equal to 1. Okay, and then the f prime graph consists of 2 line segments and a semicircle. All right, very good. Okay. So we've got all that we need for this part right now. And let's move onwards to part A to get started right here. Okay, so they're asking is that does f have a relative minimum? Okay, maximum or neither at x is equal to 6. Okay, and we need to give a reason according to that. Okay, so if we want to know if we're doing a relative min or maximum, right? So a min, so a minimum will mean that, again, we have for the first derivative of f, right? Again, we need to go from a negative into a positive on the values for that, right? Crossing that value. Again, this is going to be at x is equal to positive 6. Then the second time, if it's going to be a maximum, of course, that means we need to go from a positive down into a negative, and then neither is that f prime of x just stays at 0. Okay, all that x is equal to 6 for all three scenarios. Okay, so at that point of 6, which is that point right there on the semicircle that touches the x-axis, we can easily see that we end up at positive, hit 0, and then go back to being positive again. We are not changing the sign at all as we approach 6 on that first derivative graphs. So because of that, of being positive from 0 back to being positive, right, we can conclude that f has neither a minimum or maximum at x is equal to 6. Okay. Our work showing that we simply touch the x-axis at the point of x equal to 6 and goes back up to being positive again. Okay. So with that, we can go over to part B over here. So let's make sure we get to the next part of our... Okay, that's right there? Okay, very good. So for part B, it asks on what open intervals, if any, is the graph of f concave down. Okay. All right, so concave down, of course, right? If we were looking for that, that must mean that the second derivative of f is less than 0. Or, again, in our case, because we only have the graph of the first derivative, right? The first derivative of x is decreasing. Right? This is going to be the pointer for us on looking at the relationship between the first derivative and second derivative for us to actually make that decision. Okay? So, with that, we have our points that we need to look at, right? Again, if the first derivative is decreasing, that means the second derivative is less than 0. So we do have a decreasing segment right there, again, on the first portion of that graph from -2 to 0, right? -2, -1, and 0 there. And another section of decreasing on the first derivative graph going from +4 all the way to +6. Okay. So with that, if you want to show it in terms of the best way that the graders do it, again, the second derivative, or no, that's not it. No, they were asking the first derivative. So f of x is concave down, right, on the interval. We're going from -2 between x to 0 and from 4 all the way to +6. Okay, and that will be shown based off our work of understanding that the first derivative is decreasing, and we listed down those intervals earlier. Okay, so then going over to part C, they're asking us to find the value of the limit as x approaches 2 from both sides of 6 multiplied by f of x minus 3x, all divided by x squared minus 5x plus 6. Okay, or show that it does not exist. Okay, and we need to show obviously all of our work for that to happen. Okay, so this is quite a nice problem here, right? The limit as x approaches 2 for this function. So what we could do first is that we can just simply plug in for 2 to see if going straight ahead, right, on this limit is going to give us anything. Of course, remembering that if we get something like 0 over 0, that's going to be indeterminate, and we need more work to figure this one out. Okay, so if we try running the limit directly, that's going to be 6 multiplied by f of 2 minus 3 times 2 all over 2 squared minus 5 times 2 plus 6. Okay, f of 2 is equal to positive 1, as shown earlier at the start of the problem. So with that, it's just going to be 6 minus a 6 all over 4 minus 10 plus 6, which indeed is 0 over 0 if we fill out the work. Now, this doesn't mean that it does not exist. This means form. Okay, so what can we do then if it is indeterminate, right? We cannot determine the actual... Oy, come on, man. Are we good? Okay, and we'll have to switch that bitrate next time if that's going to be the case from now on. Fortunately, switching internet is not always the best option sometimes. But in any case, though, we have our indeterminate form again after our line of work here, that it's 0 over 0 as this part of the limit. So as a way we can do it, again, we can bring out our good friend the L'Hopital's rule. Okay, meaning that we can then, with L'Hopital's rule, is that we are taking the derivative, right? So 6 of fx minus 3x of the top and the bottom of the fraction here. So it's not going to be quotient rule in that sense, because quotient rule is a lot different than taking the derivative of the entire fraction. But by simply looking at where the direction of the function is going, if we take the derivative of the top and bottom of the fraction, just to look at the actual trend in which this function is going, we can then determine if this is going to be something that goes to a specific number or goes to infinity or something like that. So by taking the derivative, that's going to be 6 multiplied by f prime of x minus 3 all over the 2x minus 5. Again, we're still taking the limit as x approaches 2. That is not changed, right? And so now we can try plugging this in to take a look to see if this can help out in terms of us determining where our guy is going. So 2 multiplied by 2 minus 5. Okay. F prime of 2, though, is something that has been already provided on the graph of f prime, right? So that's going to be 0, as was stated on the graph. So with that, looks like we're going to reach an actual result here of negative 3 over 4 minus 5. So it's negative 3 over negative 1, giving us positive 3 as an actual limit that is defined by using Gödel L'Hopital's rule, understanding that indeterminate forms do exist, and we can use that very simple rule for us to then determine where this function is headed to at that limit of 2. Okay, so with that, we can go over to part D over here, that we want to then find the absolute minimum. Absolute minimum value of f on the closed interval. Okay, going from negative 2 to positive 8. Okay, and we need to justify accordingly. Okay, absolute minimum, of course, then means that we must look at the following, of course, is that we have our candidates, right? Okay, and then we have our actual f of x values. Again, we want to look at the lowest possible from the candidates that we're looking at as a result. Okay, candidates, of course, will mean that we look at the n values, so x is equal to negative 2, x is equal to positive 8, right? Any of those n values from where we're ending our observation could be the lowest point on the entire function. Then from there, we have some local, right? So local minimums. Okay, local minimum, of course, meaning that we need a cross, right, from a negative to the positive side, right? So from the negative side to the positive side on the first derivative graph of f, because we're looking at the first original function of f for us to make that determination, which only the graph point at positive 2 will go from negative to positive. Again, that cross there is what determines as a local, right? So right here for us is going to be a local minimum. Okay, so because of that, we have that as another candidate. So x being equal to positive 2 will be the result for that. Okay, so we have our 3 points that we can check for, and we'll take a look to see what that looks like for our original function. Okay, so f at positive 2, though, we already have that point at equal to positive 1, as shown right there at the start of the problem. So that does help us in cutting down some of our work. But now the rest of these, though, because we don't have the actual original f function for us, we only have, right? So we only have the first derivative function, f prime of x, right? We need to then go ahead and start using our good old friend fundamental theorem of calculus to then figure that out, right? So to start at fx being equal to negative 2, right? If we then took the integral going from negative 2 all the way to positive 2, a known point for the first derivative graph, that must mean that we are then going from the first derivative in respect to x, right? So by taking the integral of the first derivative, fundamental theorem will then state that we are looking at the difference of f of 2 minus f of negative 2. And so if we are isolating for f of negative 2, that means we're starting with our f of 2 point subtracted by the actual definite integral from negative 2 to positive 2 that we started out with. Of course, this being an area that we can then look at underneath the curve of the graph of f prime as well, okay, as we're taking the definite integral of f prime. So because of that, f of 2 is going to be positive 1, and we're subtracting it away from the actual interval going from negative 2 all the way to positive 2 right there, okay, which means that we have two triangles, as you can see right here. I think if we can swap colors for just a moment here, just so we can see it in its true form right here. Again, we have two triangles here, right? One on the positive side, and then this entire negative side triangle, right? All leading up to the positive 2 on the x, okay? So because of that, right, we have two triangles that we must be accounted for because of that. So let's see how that looks like if we want to calculate the area for that, being it's going to be 1/2 multiplied by a positive 2 height and a base of 1 going across from negative 2 to negative 1. And the next base going from negative 1 all the way to positive 2 will have a base of 3 and a height of negative 2 because we're going underneath the x-axis for that height. Okay. So with that, we can then go add that with the next 1/2. Again, the height is actually negative 2 and the base is a positive 3. Okay. And so that is how we can calculate for the area for that curve. Then going from positive 1, so as we subtracted by the first 1/2 times 2 times 1 is a positive 1. Negative 2 times positive 3 all divided by 2 is a subtracted by another 3 right there. Okay. So with that, this is going to be 1 minus a negative 2, making it a positive 3 as a result for the x is equal to negative 2 value. Then lastly, to complete all of this here, is that we are going to look at the x is equal to positive 8, which means that we can run the now definite integral from positive 2 to positive 8 for the first derivative. Meaning that, again, according to fundamental theorem of calculus, we are then going to then look at the difference of f of 8 minus f of positive 2. And so we can isolate for f of 8 being equal to f of 2 plus that definite integral from positive 2 to positive 8, f prime of x dx. Okay, once again, this is going to be defined as the area. So f of 2 being a positive 1 will be added to all of that area that the first derivative is looking at between the limits of 2 to positive 8, which means the remainder of the graph, again, start here, including that actual semicircle. Okay, so we've got a very interesting prospect here because the fact that if we look at the way this is divided, the semicircle is actually going to be taken away from, right? So we have the first is triangle, which is very easy to see, of course, going from positive 2 to positive 4. But then we have to keep track of that this semicircle is now taken away from the rectangle, right? As we're looking for only the heights underneath the semicircle. And we are then, if I just don't stop throwing away my own caps to my pen here, meaning that we are taking away from, in red, as you can see, right, we're subtracting the actual area of a semicircle away from the rectangle. Okay, and so in this case, let's go first with the triangle. It should be a lot easier. With the triangle, we have a height of, so it's 1/2 multiplied by a height of 2 and a base of 2, going from 2 to 4. But then we'll add this with the fact that we start with a rectangle, right? So we start with the rectangle going across from 4 to positive 8 and a height of 2. But then we need to take away that semicircle from that total area. Okay, so because of that, we have the rectangle of a base of 4 multiplied by a height of 2. But then we must subtract away from it the actual semicircle with a radius of 2. So that's going to be pi over 2 because we're taking half of a circle multiplied by the radius squared, right? Again, so in this case, if you want to take notes on this to make sure which ones are which, we have a triangle, we have we have the rectangle, and then we have the semicircle that is being taken away from that total area. Okay, so now we can deduce on our side what is going to be on that part. So 1/2 times 2 times 2 is going to be a positive 2. 4 times 2 is a positive 8. Okay, and then lastly, the pi over 2 times 2 squared is going to be a minus 2 pi. Okay, so with everything being added up here on that side, that's going to be 11 minus 2 pi. Okay, if you want to make a simple approximation, that's going to be about, well, 5. If pi was approximated to 3, just something to keep in mind for ourselves. Okay, so with that, it looks like we only have one final result for this absolute minimum, meaning that x is equal to 2 is the lowest value across all of the points for this problem. So with that, we can conclude that at x is equal to -2, f of x is well, I don't like that wording. F of x has an absolute minimum at x is equal to 2. That's what we can conclude on that side. Okay, there you go. All right, all of our work shows for it as we looked across all the possible candidates. That will be an absolute minimum. And that concludes question number 4, meaning that we are ready to go back to question number 3 and start our corrections from there. Okay, so question 3 again was that bottle of milk problem. So let's see to it how we are scoring along this. Actually, that's right. So at question number 3, we had ourselves the actual slope field, again, meaning that we are going to come across this way, right? Again, following the actual tick marks for that problem. Just to be assured of what we're looking at here is that the actual solution curve, like the one that they're showing, looks quite exactly like the one that we did on that slope field. Again, keeping sure that we are underneath that y is equal to 40 mark, as you can see with the cursor coming across there, right? We have to make sure that we are not going above that, as the question itself did state that the entire function of m of t is going to be underneath 40 for that entire section. Okay, so going back once more, is that our notebook our noted answer is going to be quite similar to that. We keep it along with the curve, making sure we're underneath that 40 mark, and that will give us full points for that. Okay, so that was simply just a 1 point on the graph, so that's 1 out of 1 correct. Okay, for that part of using the slope field properly. Again, if our camera can focus again here. Okay, so that's going to be correct for that section right there. Then going onwards to part B is that we're doing the tangent line approximation, right, for the m of 2. Okay, the m of 2 point right there. So let's take a look at how we perform, right? So by running the actual first derivative equation, we do end up with 35.4 degrees Celsius per minute. Indeed correct, that was what they're looking for. And again, from there, we can actually make the equation that the y is equal to 35/4, right? This is indeed going to be the correct tangent line equation. 35/4 is the slope multiplied by x plus 5 on the outside. Okay, so because of that, we then just put everything in terms of approximating for m is equal to 2, right? So by showing first that slope and by then approximate accordingly that it's 22.5 as the correct m of 2 approximation, that will give us 2 out of 2 correct for part B. Okay. Yep, that's all 2 points awarded there. Okay. Then over to part C here is that we are using the second derivative of this entire equation right there, such that we can then determine if it's an over or underestimate for that part. Okay, so by running the second derivative, we end up with the actual amount of that, the -1/16 of 40 minus m. I simply decided to throw that into the into a distribution right there, just to make at least what I believe my life a bit easier for that, right? Because if we plugged in for the m of the because of this, right, we can then prove indeed that we are looking at the concave down, because at the point that we were estimating that m is equal to 5, again, we end up with a negative result with a concave down, and that because we were increasing early with the 35/4 on the first derivative, we were indeed overestimating, right, the actual result of the m of 2. So because of that, both will be correct for both the second derivative evaluation and the overestimate conclusion. So that will be all 2 out of 2 correct again for part C. Okay, and so let's go lastly into our part D here, which we are using the separation of variables to then determine the m of t function entirely, with the starting with the explicit solution of m of 0 being equal to 5. Okay, so as of course they want to show that we are doing separation of variables, of the m's going all to one side and the coefficient weighting there with dt. Okay, then by running the actual integral, of course, the negative natural log of 40 minus m of 1/4 t plus c, that plus c being very important to add into as we are doing an indefinite integral as a result. Okay, then by solving for c, right, by doing our little bit line of work here, is that c will indeed be the negative natural log of 35 after plugging in the m of 0 being equal to 5 on our starting point right there. And then we do our last line of work here to then conclude that m of t is equal to the 40 minus 35 e raised to the negative 1/4 t. All of that exactly is the way that they want to see it. Okay, so with all of that there, again, they want to make the notes, of course, that you will start losing points if you don't have the plus c or if you don't do the separation of variables either. So with that, we've done everything they wanted us to do. So that's 4 out of 4 correct on part D. All 4 points were properly accounted for, meaning that the entirety of part 3 is another 9 out of 9 section for us. Good. Very good for us, at least, that we are back on track getting full points as needed on question number 3. Okay, let's move on to question number 4, and then we can get into the final section of 5 and 6 for this exam. Okay, so again, this is where we had that graph of f prime there. Okay, so part A is looking to see if we have the absolute maximum, relative minimum or maximum on the x is equal to 6 point. And of course, with our reasoning that we do not change the sign, we just go positive back to positive again, we have neither a minimum or a maximum at the x is equal to 6 point. So that's 1 out of 1 correct for us on part A, showing that we do understand what is required for us to get a minimum or maximum on a function when we have that first derivative graph. Okay, then going on to part B, they want to see where the actual part is increasing or concave down, at least for the first derivative graph. Again, we made our reasoning that if we're looking for the second derivative to be less than 0, we need to then confirm that the first derivative of f is decreasing, right? And so the intervals will be from -2 to 0 all the way from 4 to 6. Okay, and so with that concavity, we can prove that we are going to be concave down from that entire section from -2 to 0 and then 4 to 6. That is all confirmed for us. So that is 2 out of 2 correct for those correct intervals as well, to prove that with the first derivative decreasing, we are also concave down with that relationship between those two confirmed. Okay. Then going on to part C, we are doing a limit evaluation, right? So by running into this, right, because we showed that we are taking a limit for this guy at 2, again, if we do have to actually show, so that's actually very important here. Just a second. So it is actually very important to run the limit one time to show that we are in the indeterminate form of 0 over 0, right? Meaning that we both end up as an indeterminate form. This is required for us to use L'Hopital's rule. If it was not indeterminate, we are not allowed to use L'Hopital's rule at all. Okay, so that's actually very important to run it once, show that we're 0 over 0, and then use L'Hopital's rule to then figure out the determination for this function. Okay, so by doing that, we can go through, again, taking the derivative of the top and the bottom of the function, running through the math, right, of knowing how to use L'Hopital's rule, and our final result of positive 3 was exactly what we needed to show all the steps needed to get to an actual. That is 3 out of 3 correct for this part. Again, running it first to show indeterminate form, using L'Hopital's rule, understanding that it's a derivative of the top and bottom of the fraction of the limit, then running it one more time to get a whole 3. Okay. Lastly, on part D, we are looking to find the absolute minimum value on that closed interval. Okay. So we have a few candidates for ourselves over here. Okay. Meaning that, again, we were looking for the actual the absolute minimums in terms of the endpoints for this function at -2 and +8, and the local minimum at x is equal to +2. Okay, so by running through all of this, we do get the proper results of using fundamental theorem of calculus for the endpoints of +3 on -2 and 11 minus 2 pi on the 8. And lastly, of course, our local minimum showing a +1 does confirm that the absolute minimum value, again, is at x is equal to 2 at 1 as its result. Okay, so again, this is an evaluation for all the possible candidates that could be an absolute minimum, and by running through that work, we show that we're 3 to 3 correct for this part as well. Okay, meaning that we get 9 out of 9 entirely for this part of the exam. Okay, looks like we are back on track, scoring the way that we should, getting 9 out of 9 on question number 4. So let's end with questions 5 and 6 and correct them, and that will conclude it for the 2023 exam. Okay, very good. So just as a reminder, any sort of questions can be sent directly to the email labcoatmath@gmail.com for any of the viewers. But if we have everything we need right here, we should definitely go into the next problem, which includes a very lovely table for part 5. Okay, so at question number 5, we have ourselves a table. We have the x values on top, then we go f of x on one side, then after that's f prime of x, then it's g of x, and then g prime of x right there. Okay, so we have all of these coming together. X will go from 0 all the way to +2 to +4 and then +7. Okay, let's just make sure we fill out the table so we are all on the same page as to what these values are separated into. So f of x comes across as 10, 7, 4, and 5. Then f prime of x comes across at 3 over 2, -8, +3, and 6. Then 1, 2, -3, and 0 on g of x. And then 5, 4, 2, 8. So 5, 4, 2, 8 on g prime of x. Okay, a very easy table. Hopefully that will come in handy as you start answering questions. So as context here, this tells us that the functions f and g are twice differentiable. Okay, and then they get the table itself. Okay, that's just an extra note for us for context on this problem. So let's get forth to problem A here. That let h be the function defined okay, by h of x being equal to f of g of x, as right there. So then they are asking us to find h prime of 7, and we need to show the work accordingly for that. Okay, h prime of 7, thankfully, is going to be needing that we must take the note that we are doing chain rule for this part of the exam right here. Okay, so chain rule, of course, is that if we did first the h prime of x, that must mean that we do f prime of g of x right there, multiplied now of g prime of x after the fact of peeling back the layers of those two functions lodged into each other. Okay, then we can go h prime of 7 to then evaluate for that exact value. So you plug in 7 to where all the x's would go. Okay, and so we start with f prime, now g of 7, right? Now we can start using this table. So at the 7 on the x mark, g is going to be 0. Okay, and then g prime of 7, so at the 7 mark, g prime is going to be a positive 8. Okay, so f prime of 0 though, so we go back to on that side of the table at 3 over 2 for f prime. So that's going to be 3 over 2 multiplied by 8. So then we can conclude that h prime of 7 is going to be equal to, by canceling out into a 4, we get a whole 12 as a result of h prime of 7. Very simple for at least the students that do understand what chain rule really involves and how to then solve using a table. Okay, then it says that let k be differentiable. Function such that k prime of x is equal to f of x all that squared times g of x. Okay, now they're asking, is the graph of k concave down at the point where x is equal to 4, right? And we need to give the reasons for that answer. Okay, so concave down, of course, means that even though they give a second derivative of the first derivative of k right there, we need to see that the second derivative of k is going to be less than 0 at the point where x is equal to positive 4. Okay, so along with that, we can then start our work here again by taking the second derivative of k. So by doing that, again, we're still going to use chain rule once more because we're dealing now, of course, not chain rule as well. We're going to use product rule as it is two functions multiplied together. So actually, because of product rule, we might need a little more space. So let's redo the work here again. The second derivative of k will be starting here as follows. So with the, again, taking the derivative of the first part and then the second part. So by bringing down 2, that's f of x multiplied by f prime of x times g of x as the first part of product rule. Then we're going to add that with the second part of f of x, all that squared, leaving that entirely alone, multiplied by g prime of x. Okay? That is how we're going to use the product rule to get to the second derivative of k. But then they're asking at x is equal to 4. So we can then plug in for 4 for all of this. So it's f of 4, f prime of 4, multiplied by g of 4, plus f of 4, now all of that first, then squared, times g prime of positive 4. Okay, so now we can then plug in for all of these, which can be easily found across all the tables here. So let's bring that up for us to then make our deductions here. So f of 4, so f of 4 is going to be a positive 4. F prime of 4, so f prime line going up 4 is going to be a positive 3. Then g at 4 is going to be negative 3. Okay, adding that with f of 4, so back to that again is a positive 4, but all that will be squared first. And then g prime of 4, so g prime at 4 is going to be a positive 2. Okay, so it looks like we have all of that all listed out here. So then we just need to go and solve for that. So we have 8 times a negative 9 of those two then multiplied together. It's going to be a negative 72. And 16 times a 2 will be a positive 32. Okay, this ends up with a result of a negative 40, again, which is the k double prime at the positive 4. Okay, again, because of that, All right, they're asking, is it concave down at x equal to 4? And because it is indeed negative on the second derivative, right, we can confirm that yes, right, k double prime of 4 is concave down. Very nice. Okay. Just a few lines of work on the first derivative, but that is exactly what we need for us to then find all of that on this part of the problem. Okay. Moving on to part C, it's saying that we must let m be the function defined by m of x being equal to 5x to the third, okay, plus the integral going from 0 to x of f prime of t dt. Okay, so that's all written right there. Then it's saying that we must find m of 2, okay, as that part of our directive here. Okay, so very easily, if we wanted to plug in for 2, so m of 2 is equal to 5 2 to the third power plus the integral going from 0 to 2 of f prime of t dt. Okay, meaning we have to go ahead and use fundamental theorem of calculus because we are taking the integral of the first derivative function of f on that side. So by first doing the exponent of this, was 5 multiplied by 8. And so because of that, again, understanding fundamental theorem of integrating a first derivative, that means that we are looking at the original f function, bring it back a step, of f of 2 minus f of 0. 2 points, which can be easily found on the graph, or on the table that was given earlier. So we get a whole 40 plus f of 2, and f of 2 is shown right there on that part of the graph, is going to be positive 7, and f of 0 is going to be positive 10, respectively. So we can put that as 7 minus a 10. Okay, so that's pretty straightforward. So we can put in the last lines of work here, meaning that we get a positive 37 as a result of m of 2. Okay, very good. All right, so that would conclude our work on part C. Then part D will then ask us for, is that is the function m defined in part C, increasing, decreasing, or neither at x is equal to 2. Nope, 2, and then the question mark. Okay, right? So are we increasing, decreasing, or neither at x is equal to 2? Okay, so given that the function m that they're talking about, again, increasing, decreasing, means that we are looking at m prime of 2, and that's what they want us to find in order for that to be shown properly. Okay, so with that, if we took the first derivative of m in respect to x for this part, that means that we are going to bring down, right, starting from the 5x to third power up there, it's going to be 15x squared plus, again, fundamental theorem was once more going to dictate for us what's going to happen if we took the derivative of an integral, and because only one of the limits is going to be an actual variable, that means we will substitute that back in as f prime of x right in there, and that will be the first derivative of m using fundamental theorem quite easily right there. Okay, so then if we then plugged in for m prime of 2, we can then see what our answer results in. So it's 15 multiplied by 2 squared plus f prime of 2. Okay, so 15 times 2 squared will be a positive 60 plus f prime of 2, which f prime of 2 right there is going to give us a negative 8 as a result of that. Okay, so 60 plus a negative 8 will give us a positive 52 as a result. Okay, so because of that, right, this will then conclude that because we are positive on that first derivative, we are then increasing, right? So m of x is increasing at the x is equal to positive 2 point that they were asking for at the start of the problem. All right, very good. So that will be problem number 5 using that table in which they gave us at the start of the problem. So let's get to problem number 6 and let us finish strong on this now packet of, oh, that's not it. I need to get to another page. Okay, so we'll be finishing up here with problem number 6, and let's copy down what they have for us on here. Okay, so they tell us that we have the equation 6 times x times y is equal to 2 plus y to the third power. And that's it. That's all the context they're going to give us for question number 6. Very interesting. Okay, but nonetheless though, let's see if I straighten this all out here. I keep hitting my camera. But with that, part A will ask is that we want to show that the first derivative dy over dx is equal to 2y over y squared minus 2x. Okay? So now they want us to put all that work all together to show that we are dealing with this properly on the first derivative. Okay? So with that, we can then go ahead and start putting on the derivatives here. So again, so 6xy is equal to 2 plus y to the third power. We take all this, right, and we take the derivative in respect to x for all of these guys, meaning that we need to start doing implicit differentiation. Okay, so with that, we can then start putting all this together. So first we have product rule, right, and with the y cubed we have chain rule. If you want to make those notes, just to make your life on implicit differentiation a little bit easier before you rush headlong into a bunch of unknowns into this problem. So because that product rule will then show that it's 6 times y plus, now the y derivative is going to be 6x times dy over dx, and that's going to be equal to the 2 going straight to 0, plus y cubed is going to be 3y squared, but with chain rule, because y will now be derived into dy over dx, that is very important to leave on that side. Okay, so because of that, we can then start grouping where the dy's over dx's are. So this guy can move over to the other side. So there's 6x dy over dx. So we can factor out a dy over dx to be isolated, meaning that we get 6y being equal to 3y squared dy over dx minus 6x dy over dx, like that. Okay, so from there, we can then factor out with the 6y on the left side, the dy over dx of 3y squared minus 6x. Okay, very nice. So because of that, we can then finally isolate for ourselves that indeed dy over dx will be equal to, by this being sent over to the left side, that it's 6y all over 3y squared minus 6x. And with that, because a 3 is actually a common factor amongst both the numerator and the denominator, we can then simplify that out, a positive 2x right there, and those will cancel out, meaning indeed we have shown that 2y over y squared minus 2x is achieved by taking the first derivative of that equation. Very nice. Okay, so then going on to part B, it says that find the coordinates of a point on the curve at which the line tangent to the curve is horizontal. Right? Okay, or there's no points, but nonetheless though, right, we should have enough here at which the line tangent to the curve is horizontal again. So the line tangent being horizontal, meaning that we have our first derivative dy over dx that we've already shown before is equal to 0. Right? That's what they want to see for this part. Okay, because of that, then if we look back at the equation here, so 2y is y squared minus 2x. Again, if that's going to be equal to 0, only the 2y must be equal to 0, meaning that, right, that if that were the case, right, that just needs to show for us that we must be equal to y is equal to 0, right, for that part, And that is still acceptable for the lower part of that derivative on the denominator. And so we will plug that back into the original equation. So 6 times xy is equal to 2 plus y cubed to look at any x coordinates that will be possible to be matched with that y coordinate. So with that, 6x and 0, 2 plus 0 to the third power. And we run into a roadblock right here. Okay? Because the entirety of the left side is equal to 0, and we left with 2 on the other side, obviously this leads to a false math statement that 0 is not equal to 2, right? So even though y is equal to 0 would work for a horizontal tangent line, because we end up with an incorrect math statement on that side, right, that will conclude that no points on the curve have the line tangent horizontal. Okay, and that's what we can confirm, right? Our work shows that we must have y is equal to 0 as a value on the first derivative to prove that we are horizontal, but according to that as well is that because we have no appropriate x values to make any sort of points such that that will be the case, we then have to conclude that no points on that curve will actually be horizontal in the first place. Okay, with that we can get to part C here, that we must find the coordinates of a point on the curve at which, this time though, so might sound very similar, but it's at which the line tangent, this time not horizontal but is vertical, right? That is going to be the main difference right here between part B and part C. Okay, vertical then means that the first derivative dy over dx, in this case, right, again, vertical in the sense of a vertical slope, right, that must mean that we are dealing with an undefined slope. Okay, in this case, right, going back to the first derivative equation, right, is that the denominator is equal to 0. Okay, right, the denominator of the function must be equal to 0 if that were to be the case. Okay, if our camera can very easily focus on that. Okay, so with that we must show that y squared minus 2x is equal to 0 first. Okay, meaning that we have the relation that y squared is equal to 2x as a result. Okay, so if that were the case, we can then start putting through that x must be equal to y squared over 2, and we can start looking at some possible solutions for this part of the graph, right? So going back to 6x times y is equal to 2 plus y to the third power, as was the original equation, for us to look at those points. If we then plugged in that x being y squared over 2, so 6 y squared over 2 times y being equal to 2 plus y to the third power, we then end up with a result of 3 times y to the third power by multiplying those across, okay, being equal to 2 plus y to the third power. By subtracting y to the third power, that means that we get 2y to the third power being equal to positive 2, making y to the third power equal to a positive 1 after that fact. And then we end up with y being equal to 1. So now we need to know what the x values will then be. Okay? Very simply, we take that y is equal to 1 and we plug that right back into the equation to solve them for x. Plug in 1 there, so 2 plus equals to 2 plus 1. Okay, so 6x is equal to 3, so then x will be equal to 1/2. Okay, so y is equal to 1 and x is equal to 1/2. That will be one of the points in which that would be the case, right? Does that match with our denominator of our first derivative still being 0? Let's take a look here, right? So you get 1 squared minus 2 times 1/2, and that is still equal to 0. And again, this is an undefined slope, given that we are dealing with the denominator of the dy over dx equation from the start of the problem. Okay, very good. So with that, we do have the coordinates, right? So let's see, the curve has a vertical tangent line at the point 1/2 on the x. Make sure to order that properly as a ordered pair of coordinates that they will grade for us. Okay, very nice. So let's finish this off at part D here. That's saying that a particle is moving along the curve. Okay, at the instant when the particle is at the point 1/2 comma -2, its horizontal position is increasing at a rate of dx over dt being equal to 2/3 units per second. Okay. Then the question itself is that what is the value of dy over dt at that instant. Okay. We've got a lot written out for us right here. So let's see to it what they are really looking for on that point. Okay. So at that point 1/2 comma -2, okay, they want to go ahead and see to it, at least on their end, what that will look like in terms of the let's double check here. Yeah, okay. Yep, so that's still fine. So yeah, they're looking to see where the actual value of dy over dt is going to be at that moment. Okay. So because now we are going back to the original equation, again, we want to look at dy over dt and dx over dt, right? We need to go ahead and start looking at derivatives for this equation. So 6 times x times y is equal to 2 plus y to the third. But now instead of taking a derivative in respect to x, we are taking a derivative in respect to t. So again, this is implicit for both x and y, right? Okay, so neither x nor y will go to 1 if we were to go and take the implicit differentiation across this entire equation, because we need everything in terms of dy and dx over dt for both directions. So going back to it, we need to go back to doing product rule once more. So 6 times dx over dt times y plus the 6 times x times dy over dt is equal to 2 plus 3y squared dy over dt. According to chain rule, again, it should be fairly simple as we've done most of the work already. It's just that the x itself will now go over dx over dt on that side. Okay, the 2, of course, in my work needs to go to 0 because of that, because we are taking a derivative. Okay, so in this sense, we just need to then isolate for dy over dt because that's all that we need to look for on this side. So because let's move over that 6x on the other side. So 6 times y dx over dt will then be equal to 3y squared dy over dt minus 6x dy over dt, like that. Okay. Then by factoring out the dy over dt, we can end up with the next line. I wonder if we can be ambitious enough to shove that right there on the bottom, but I think we should be fine. 6y dx over dt will then be equal to, by factoring out dy over dt, it's going to be the remainder of 3y squared minus 6x on that side. Okay, and so we can then isolate for that dy over dt that we are looking for at the start of the problem to be equal to the 6 times y times dx over dt all over the 3y squared minus 6x. Okay, so remember we have the point x comma y at the start of the problem and the dx over dt value, so it looks like we have everything that we need to then plug right into that first derivative. Okay, so with the point that we're looking at, so we had 6 times y of negative 2, dx over dt was 2 over 3, and then we have the denominator of 3y being negative 2, but all that is squared first, and then minus 6 times 1/2 from the x. Okay, so this looks like we just need a little bit more algebra just to be able to figure out. So we have a negative 12 on the top there, multiplied by 2/3 makes it a negative 8. Okay, all divided by, so make sure we're continuing to work there. So again, that's going to be positive 4, so that's a positive 12 on the first side. Again, the exponent comes first. Minus 6 times a 1/2, which would be a 3. Okay, so it's negative 8 over a positive 9. Okay, and that'll be units per second, again, on the vertical distance. All right, good. So that looks like a pretty nice answer for us. Again, we're just making sure that our math stays consistent because we are looking at dx over dt and dy over dt in the same equation, meaning that we're going to do implicit for both x and y for the d over dt derivative. And so with that, with a little bit of algebra work and plugging in with the point and the first derivative of x given to us, we then could find what the change in the y units will look like. Okay. So, yes, our viewer Meeting says she understands the algebra part. That is very good. Yes, very good that our students are indeed keeping up with some of the parts of this exam. But with that, that actually will conclude for the exam itself. So let's go back to part 5 here so that we can then start correcting and see what our total score will look like. Going back to the question with that very large table for ourselves here. Okay, so question number 5 here is talking about, first we want to see the function of h. Again, they gave us that equation h known as f of g of x, and they want to find the exact point of h prime of 7. So good old chain rule is going to be used. That's exactly what they want to see, for us to remember how to do that kind of derivative. Then by plugging in 7 after the fact, we get a positive 12 of h prime of 7. That's 2 out of 2 correct for us on part A. Very nice. Okay. Then part B here is going to be looking at the differentiable function of k prime of x that they gave us first, but because we're looking for something that's concave down, we must then know what the second derivative will look like. Okay, so by doing that, we get the entirety of the second derivative of k. It looks a little bit messy, but the work still checks out that it's 2 times f of x multiplied by f prime of x multiplied by g of x plus f of x all squared multiplied by g prime of x. Again, that was the result of product rule from both of those parts on the k function. This result is exactly what they were looking for us to do the derivative properly. Then, simply by plugging in the 4 and getting the final result of negative 40 as a result of the second derivative of k at 4, right? That's what they want to see, to show that we plugged everything in properly to get that result. Then our reason, of course, is that yes, indeed, it is going to be concave down at that second derivative point at x is equal to 4 that they were asking for. Okay, so then we go over to part C over here, that they are looking for the function m of x is equal to all of that, the 5x cubed, and that lovely definite integral going from 0 to x for the first derivative of f in respect to t. So then, by showing that we want to find m of 2, right, we can simply start plugging that in and looking at with fundamental theorem to understand that we are looking at the difference between the 2 points f of 2 and f of 0 by integrating the first derivative of the graph. And so we end up with 37 being the actual point. Part C was just a 1 out of 1 correct, that they were looking to see if we can back up our work with that problem. Okay. Then lastly, at part D over here, is that we are looking at the function of m defined at part C that we were talking about earlier. Again, were we increasing, decreasing, or neither at the x is equal to 2 point? So with that, we then, of course, need to take that first derivative of m. That's exactly what they want us to consider. that's what we need to do to determine if it's increasing or decreasing at that point. And then because of that, we start putting everything together, understanding how fundamental theorem will work, that we're looking for f prime of 2 as a result of that. So us getting a positive 52 as the end of that work, we can then justify that it is indeed increasing at x is equal to 2 because it's positive on the first derivative. Okay, so with that, that's all 3 out of 3 correct for that part, giving us a total, once more, of 9 out of 9 on question number 5. Very good. So, looks like we're on our way to redeeming ourselves from our earlier mistakes with some sad faces at questions 1 and 2 because some very sad plugging in and reporting the answers from our calculator. That could be seen on the recording of this live stream, where I'm sure that would be easily laughed away by other calculus students. That should not be repeated on the exam. Nonetheless, though, let's finish this off with the question number 6 answers. So we have that, again, all the context they actually gave us was literally just that equation of 6xy plus 2 is equal to 2 plus y to third power. So part A was that we needed to show the work of the implicit differentiation. Again, this line of work right here of understanding that x is turned to 1, right? So the x's will go to 1 from the derivative, but y's will go to dy over dx following product rule. So ending with that, that will be the first check that they want us to have. But then the last verification, of course, is that we show our work to lastly end up with 2y over y squared minus 2x, the way that they asked us to confirm that the first derivative was exactly what they needed. So that gives us 2 out of 2 correct again on that part. Okay. Then part B is that they want to find the coordinates at which the line tangent of the curve is horizontal, right, on that point. Now, again, because of the fact that horizontal line means that the first derivative must be equal to 0, that must mean that only the numerator, right, so numerator in that fraction for the first derivative must also be 0, meaning that the point will be y is equal to 0, but this is where the but comes in, is the main issue is that if we plugged in to find the x coordinate on the original function, we end up with a false math statement that 0 must then be equal to 2 for that point to exist. Of course, because it's a false math statement, no value of x would satisfy that first derivative being equal to 0. So we conclude that there is no point in which that the line tangent of that curve is going to be horizontal. So because of that, that is 2 out of 2 correct for that part. Okay. And so lastly, next up, we'll go over to part C, right? Well, that to then show if we are looking at the similar thing here, where in this case, they want to know a vertical tangent line instead, right? So because of that, the result of it being a vertical tangent line is that the slope must then be undefined, meaning that in this case, only the denominator, right, of that first derivative equation, right, so the denominator must then be equal to 0 because of that. Okay. So, yes, sending love from Jamaica. Yes, very interesting that you would say that, but we'll see. We'll check the messages. I know you messaged me earlier today, Nicholas, but we'll have to see what you mean by that. But nonetheless, though, that means that we're still going with our conclusion that the denominator must be equal to 0 to get an undefined slope for that tangent line to make it vertical. So with that, we then realize that we end up first with the part that we can isolate the x because we have an equation of y squared minus 2x being equal to 0. We can then plug that back in to our original function, right, to make everything isolated in terms of y. And so we end up with y being equal to 1. Plugging that back one more time into the original equation to find the x coordinate, we get the coordinate pair of 1/2 on x and positive 1 on y. Okay, so because of that, we do end up with a proposition this time for a vertical tangent line, meaning that our justification is going to be correct at 1/2 comma 1. There is a vertical tangent line for that equation. Okay, so with that, 3 out of 3 is going to be correct for part C. And so let's end this with part D right here. Okay, so that with the particle moving along the curve, again, we're going to add the time component of dx over dt. And so in the case, they're asking for dy over dt in the same scenario. Okay, So because of that, we then need to actually go use implicit differentiation on both x and y because we're differentiating in terms of t, right? Meaning both x and y will have the derivative component of dx over dt and dy over dt in the same equation. But because they gave us dx over dt at the start of the problem, we are meant to isolate for dy over dt, as our work showed, ending up, right, with the differentiation ending up with this equation, right, of dy over dt, as shown right there. Then we plug in for everything that was known, the y's and the dx over dt, which was known there before. And so by putting everything through, we do end up with the actual dy over dt value of -8 over 9. Okay, so they want to make sure that we understood that we are doing implicit differentiation in terms of t, and our final result of -8 over 9 was also the correct answer. So because of that, that's all 2 out of 2 correct for that part as well. Meaning that with everything else correct, we add up once more to a 9 out of 9 correct, okay, for this question as well. Very good. So with that, we ended up very nicely and strong. This was wonderful, right? At least with our ability to stay consistent and get the last stretch of the problems all perfectly done correct. So out of a total of 54 available points, we scored 52. I'd say that's pretty nice, as we kept ourselves from making any more mistakes on the non-calculated section. So to show for right now here, if we wanted to convert this over to a percentage, we will be looking at a percentage of 52 over 54, and by multiplying by 100, we end up with a percentage of 96.230 if you round it to do decimal places, right? I say that's pretty nice for us on this exam. Okay, so with that, we actually have, well, if we're continuing forth, yeah, we have the 2024 exam. This is a 2023 exam, so the 2024 exam will be waiting for us, as the actual AP exam is approaching very fast for the rest of our students here. So again, this was a pretty nice exam to go over. There really was just a couple of simple mistakes. There wasn't any real issues explaining the rest of the concepts. So with that, that really should just about do it for today. Again, I think we made pretty good progress over all that we went over for this exam to be successful. So with that, that should be about it for today on the 2023 AP Calculus exam. And we'll be back again on Thursday at 4 p.m. Pacific for our viewers once more to go over the next exam. So again, I know that there are a number of viewers that will return back. Yes, thank you for the applause, Nicholas. And we'll be making sure to return once more to our loyal viewers again on Thursday as we continue forth with our practice. So with that, again, I know there are other viewers that watch the recording of the stream, so we'll conclude it here for today. And all this will still be left online on our YouTube channel, as we'll be coming back on Thursday. Thank you all for tuning in, and we'll see you all on Thursday.